Hello everyone. Today we are going to discuss the system design of Leetcode. This is a assignment from the ChaiCode System Design Cohort. And today, with this problem, we are going to have a lot of fun discussing the different ideas and different techniques where we'll learn how to implement this. So, if you don't know what Leetcode is, it's a platform where you have uh, a list of problems that are based on data structures and algorithms, and you'll see a lot of problems. Like here you see it's around 4,000 problems. So you can submit your solutions, and you can just practice all those DSA problems here. And if you try to select one of these problems, you can load one exact problem with all of its description, some sample test cases, some constraints, and all the relevant information. On the right side, you get the option to submit your code, and once you select a language, write your code, and you try to submit, that's when you get a status that if the solution worked properly or it failed due to some compilation error, runtime error, or time limit exceeded or memory limit exceeded. So all these things will be discussing, and once you get to know what are all the requirements of the system, then you will start to think how it can be built. So, like I said, let's start with the requirements. So, the first requirement would be that the user should be able to fetch the problem list. So, that's what we saw here, problem list. It will have a list of all the problems, and a good idea here would be to not load all the problems at the same time, because that would be uh, a little like straining on the database. Second should be to load a specific problem like we saw here, and then load the relevant related data like the test cases, constraints, anything that we see here on this. Okay. The third option would be the user should be able to submit. So once we are able to submit the problem, we should be able to see the results in the future as well. So if you see here, we have a lot of submission history in the past where I have submitted some problem, and it shows the runtime, language, with memory, and any related metadata. So stuff like this should be able to we should be able to retrieve. And let's say you want to practice and compete with others, there should be a contest, and in that contest you'll be seeing your ranking compared to other people. That's also called a leaderboard. So when you compare with others, you'll see how you can uh, compete during a contest, and in that time constraint, uh, how well do you perform. So here you see the ranking of the person, whatever is the score, and any related data, how much time each problem took. So stuff like this is stored in a leaderboard. And we can say a generic thing that's always there in most of our projects, that is authorization. So not any unauthorized user should not be able to log in to this to our account, let's say. And there should also be a rate limit. So a freemium or a free user, they should not be able to submit too many problems, and they will have a lot of restrictions on the things they can do on the platform, as compared to any uh, premium user. They are paid users, so they'll have more features. Okay. So here we have a sample explanation of how a problem will look. So we'll have a problem statement, test cases, any related images. So sometimes there will be explanations using a description, graphic description, and any metadata like how many people have liked this problem, or if there is any company related information. So all that we can store in the database. So let's get on with the design. So like we discussed, we'll have a lot of endpoints in our application where user can fetch the problems, or they can fetch a specific problem, or they can submit a solution, or they can get the leaderboard during a contest. So let's see the first API, that would be problems. So like I mentioned, there should be some kind of pagination involved in this, and we should be able to fetch only a set of information or set of problems. Like if there are 1,000, we will not be loading all 1,000 at the same time. We will be loading only 10 at a time or 20 at a time. So that thing we can explain to the user, or in the UI they will have the option to set how many they want to load at a time. So, and we can also set it as per our constraints that we have set in our backend. So in the second option, or the second API, we have problems. So a problem will have a problem ID or a name, however you want to define or store that problem and retrieve it from the database. So when a user uh, fetches the details from a problem, the request passes through a API gateway that will do all the load balancing, all the authorization checks, and all the rate limiting here. So we can set up all of that in our API gateway. So as I mentioned, load balancing. So that also involves having multiple instances of our server. So here I have given a sample Leetcode server. It has multiple EC2 instances. That's our machines or VMs, and all of it's in a auto scaling group. So whenever we want more instances, we can start up a new server, EC2 server, and then that will also start serving our customers. So API gateway will be able to route the traffic to that. So when we fetch the details of the problems, so we, before checking in our database, we can introduce a cache. So if it's static data, all of it can be cached in our Redis instance, and it can be easily retrieved and sent back to the user, decreasing the load on our database. And let's say if it is not available in our cache, it's not a like highly referred to problem, we can directly fetch from our database, and then if needed we can store in our cache. So here we can discuss a lot of strategies that will be there for a cache, like LRU cache, or when the eviction will be done from the cache, what will be TTL for a specific problem in our cache. So all that we can discuss here. And let's say we implement a LRU, that's least recently used. So whenever we have the size of our cache filling up, we can evict one of the problems that is not used as recently or as frequently. So that would be least frequently used LFU cache. So once we have that setup done, we can reduce the load on our database. So what other things we can store in our database? That's the complete problem set that will have the URLs for the images that are related to that problem, all the test cases, all the user data. In the user data, we can have the uh, we can say a website level ranking of that user, how many problems they have solved, how many days they logged in. So all that would be a future discussion, that the streak that they maintain. So like an example of a streak would be how many days in a year the user has logged in and submitted a problem. So all that, it's just information you can store in a DB, and if you want you can discuss it with the interviewer as a point you can mention as a future enhancement. But let's not dive into it, because when we discuss a system design problem, our scope should be limited to the requirements and what would be the core of the problem. So when we say lead code, the core of the problem is the code execution engine. When we say social media platform, then it would be the workers uh, that process the images, upload the images, and then if it's a streaming platform, then the workers that process video and then convert it into different formats. So stuff like that. So here let's focus on the code execution engine. So the third API that we'll have is the post. So when we want to submit a problem, for that we will have the problem ID and the code that the user wants to submit and the language they selected. So using this language, when the request comes, we will enqueue that in our submission queue. So here I've just given an example of SQS, simple queuing service from uh, AWS, but we can use other queues as well. And we have a worker pool where one of the workers will pick up the summation. So this job, when it is picked up, it will decide which ex- uh, which language it is, and then using that language it will try to uh, execute it. So let's move on to our code execution engine. That's the main place where the all the fun happens. So let's see. So there are a lot of security constraints on the code execution containers. So each of these are containers. They are sandbox. They don't have any access to the network. They don't have any access to file system or the any other system calls, and they have a fixed runtime. So after, let's say, 2 milliseconds, sorry, 2 seconds, there will be no the execution will stop by itself, and the result would be that time limit exceeded. So the user will get that as the result, and they will have a fixed CPU and memory allocation. So if they exceed that allocation, they will get a memory limit exceeded. So the user uh, waits for their execution, but while waiting, they don't know if the result is if there is any change in the result. So instead of making them wait for it, and they don't know, we can show a loading icon, and in the background, uh, when we submit a problem, the server returns a ID and saves it to the database. So using that ID, a user can do a get request and check the status of that submission ID. So it will retrieve that status, and this process is called polling. So the user can poll for the latest status of their submission, and when the submission is complete, we send the result back to the Leetcode server. It updates in the DB, and when the user polls next time, they can get the result. So here the code execution engine, it's up to us how we want to implement it. We can have a AWS Fargate setup where we can spin up new instances as per our requirement. We can also keep some instances of the containers already present. So here I've given an example of Docker container. So we can have, as per language, uh, multiple containers. We can see how many submissions there are for C++, and based on that we can keep always some number of containers always running. There is also a platform called Jet Zero. It's an open source tool where it handles all this code execution, creating of containers, sandboxing, access to the network and system are restricted. So whatever we want, and even the destruction of those containers. So it's a use and throw kind of thing when we have a single container. So we cannot use it again for another execution. That's why we want to spin new instances fast. So this thing can be handled by either Judge Zero or AWS Fargate. So let's do a little more deep dive of how the leaderboard would work. So let's say there are multiple clients or users that are uh, in ongoing that are in a ongoing contest, and they want to get their ranking, and they want to see the leaderboard. So what will happen is whenever they submit a problem, we have seen they poll for their results. So when the result from the worker is sent back to the Leetcode server, it gets updated in the database. And as along with it, we also update it in our cache. So this cache, let's say it's Redis. So Redis has a functionality to sort the data by a key, and that's called Z set. So we can store that in the database as a source of truth. And when the all the score and other related data for a user is in a database, along with it we also update the cache, and it maintains our leaderboard, and we can save that information and send it back to the client. So this will allow us to order the data, and because ordering the data, doing a same query again and again to the DB will not be good for our DB. It will stall our DB, and it can even bring down our DB in case of a thundering herd like situation where a lot of users are trying to access the same thing, and they're all trying to execute the same kind of query where they want to fetch a leaderboard. So why would we want our DB to execute the same queries again and again? That's why we introduce a cache. So using this, we can maintain a leaderboard like this. So whenever a new submission is there, it will execute again and save the data to the DB. And then once the data is in the DB, we can also save it in the cache. It will rearrange itself using this ordering, and then return the data back to the user. Let's also see the submission pipeline again. So when the user submits a solution to a problem, it the code data and other related data we also save in our database. They get a submission ID back. Once that submission ID is given to the client, they can continue polling for the status. When the data is already saved in our DB, we also submit it to the submission queue. So it's a job submission engine we have created here. So we'll have a worker pool which will pick up one of the uh, submissions and then pass it to the code execution engine. Here it will run the code in a specific environment, let's say for C++, where it will compile the code, run it again, test cases, and then prepare the result. So that result is sent back to the worker, which will send this result back to the server, which will update it in our DB and then send it back to the client when they poll for the result. So in that case, the user will see some kind of submission result like this accepted in their system with any relevant details, that memory, runtime, anything, that all can be handled in our low level design. So that's all we had for our design for Leetcode. I hope you understood, and if you have any doubts, please feel free to add a comment and ask me. I'll be happy to answer. Thank you.